Hey everyone, welcome to the third lesson for this week. So far we've covered completely randomized designs in terms of ANOVA and contrasts. Today we're going to be talking about multiple comparisons. This is a post-ANOVA test, which is going to be a little bit different than contrast. So contrast, we had a specific comparison. Multiple comparisons is when we don't have a specific comparison, but we want to know about all the pairwise comparisons. So the goal may be just to determine if all the treatments are different from each other, and that is looking at those pairwise comparisons. What multiple comparisons does for us is it provides a way to preserve the statistical validity of our inferences when more than one inference is to be made on the same data. So again, multiple comparisons, the goal is to make all pairwise comparisons. So if we took the number, how we find the number of pairwise comparisons is by represented by m, and it's going to be equal to the number of treatments times treatments minus 1 divided by 2. So if we looked at a simple example where we had 6 treatments, we'd be left with 15 pairwise comparisons. Now, if we wanted to carry out some inference procedures for all of these comparisons, then the type 1 error rate, which recall type 1 error rate is the chance we reject the null, saying there's a difference when really we shouldn't have rejected the null, i.e. there's no difference. And so if we were to do all these pairwise comparisons, then the type 1 error rate can escalate. This is the problem that led us to the idea of ANOVA in the first place. So rather than performing several individual t-tests, we perform an overall t-test. Okay. Now, to really talk about this more, we need to talk about two different alpha rates. The first one is our individual test-wise type 1 error. This is the alpha level we're accustomed to setting, typically at a 0.05 for each individual hypothesis. And this is what we're accustomed to when we're just doing a single comparison. However, when we have a single ANOVA analysis, we are doing a lot of hypothesis tests within it, and we can have an experiment-wise type 1 error rate. Okay, this is going to relate back to the individual test-wise alphas, and so our alpha E is our overall error rate for all the tests. I'll have an example a little bit later on that might be able to clarify that a little bit more. And so in a lot of the cases, we want to set our overall type error rate for the tests and then determine our individual. So now we're interested in doing this simultaneous procedure versus doing each individual test. All right. Now with multiple comparisons, there are about 10 to 15 procedures that are really famous, where 6 of those are used on a regular basis. For this class, we will be focusing on Tukey's honestly significant differences, or Tukey's HSD, and Fischers least significant difference, or Fischers LSD. In JUMP, it's referred to each pair student T's. This should be a review from Stat 5615 again. All right, let's start our conversation with talking about Fischers. So to utilize Fischers Method, we first perform the overall F test, which we learned about in Lesson A. And if this test fails to reject H naught, that is, we declare lack of evidence for a difference in the means, then we do not continue. And so pretty much what we're saying is there's no evidence that they're different, so why would we want to then ask the question of which ones are different? However, if our test rejects H naught, i.e. telling us, hey, there is a difference, then we will perform it. So the overall ANOVA F-test is kind of almost acting as like that initial screen to protect us from doing a bunch of t-tests. There are some drawbacks in which the ANOVA test gets it wrong and creates a type 2 error. So what I mean by type 2 error is that there is a difference between the means, but our ANOVA test fails to find it. Now, type 1, type 2, this is a type 2 error. For type 1, type 2 error, in our next lecture, I'll re-provide those definitions. So if you're not recalling these right away, next lecture, I'll talk about these definitions again. Additionally, Fischers doesn't tend to do well if the population means are all equal, but like 1 or 2 are different. Okay. So unlike Fischers, who use the Fischers method, which is going to use a standard T, Tukey's is going to use a different distribution. And that distribution is going to be the standardized range distribution, and it's typically denoted with a Q. You don't need to know those specific details, but I gave it to you guys just in case you were interested. This is also one of the better methods because it's not overly conservative, and it's going to provide a good power for detecting difference. We will talk more about power next lecture or next lesson. Okay, so if you can't recall the definition, we'll talk about that in the next lesson. Also, when all the pairwise comparisons, plus you don't have too many constraints or interests, this method will, again, have good power. So what I would suggest is that for your research, go and investigate some research papers or the journal you're going to look at to see which one they prefer. That would always be the best method of figuring out, do I use Fischers or do I use Tukey's? Now, just to give a quick comparison of the two different methods, let's look at this little table I made right here. And so let's say we have 3 treatments, A, B, and C, and we want to compare them. And how it works is Tukey's is going to set our experimental error first. So Tukey's is going to set this first to that should be 0.005. I'll change that on y'all's notes. All these should be 0.05. And then we're going to set our individual alpha rates to be less than 0.05. So that when you add them together, they accumulate to our experimental error. Fischers is a little bit different, in which you're going to set the individual at 0.05, and then the experimental error is going to be larger than 0.05. I will fix that on y'all's notes, so don't worry. Okay, the thing about having this higher overall type 1 error, so Fischers is going to have a higher overall error, i.e. right here, than Tukey's, which is going to make it more powerful. And again, we'll talk about power in our next lesson. All right. Now that we've talked about multiple comparisons, let's see how we can implement this on our bologna texture example. Again, this example was comparing 12 mixtures, and our goal was to see if there was a difference between the mixtures. So we had our ANOVA table here, and we've concluded that there is a difference in the mixtures. And so now the question is, which mixtures have significantly different texture measurements? And so we answer this by using our Tukey's honestly significant difference method. Now, I provided both jump and R. In this case, I actually prefer jump's visualization. This is what we would call a ordered letter report, and it looks a lot cleaner than what we would get from R. So let's figure out how to read the jump input, and then we'll talk about the R. So how we read this is the levels not connected by the same letter are significantly different. So if we look at levels 4, 5, 1, 4, and 5, these are not significantly different. But levels 1, 4, and 5 are significantly different than 2 through 9, or the rest of them. Okay? Another way we can look at this is we can look at right here. 3 and 9 are significantly different than 8, 6, 10, 11, 7, 2, 5, 4, 1. So it's all about, are these letters connected? If the levels are connected, they are not significantly different. If the levels are not connected by the same letter, they are significantly different. How you would read this in R, which is a little bit different outlay, would be looking, so right here, this hypothesis test is comparing 2 and 1, and we see that we have a p-value a very low p-value. So we would reject the null that these two are similar. How that relates is if we look back here at 1 and 2, they're different, and that's also what this is telling us. Okay, now let's have a p-value of 1, and this is comparing 4 and 1. And we know from jump, hey, they are not significantly different, and that's what our p-value is telling us here. This is 1 and 4 are not significantly different. So this example had a lot of different treatments. If I was to break this down just a little bit for you guys, and we just say we have 3 treatments, so we'll say level 1, 2, 3. One thing we could get, or one result could be A, in which this would represent no difference. We could also get another result. Again, this is different, so I'm going to put it in a different color. We could get A, B. So level 3 is significantly different than 1 and 2. 1 and 2 are about the same. Or we could get a third kind of look at this, and you could have A, B, C, and all 3 of these are different.